So we've been talking about nucleophilic aromatic substitution and electrophilic aromatic substitution. And there are a couple of more reactions of aromatics that we need to discuss that sometimes fit within these two categories, but otherwise sometimes do not. And so the first reaction that we want to talk about is the nitrosation of aromatic amines. Let's start with this molecule aniline. So aniline is an important benzene derivative that can react with nitrous acid to produce a nitrosamine. All right, so let's say we were to take nitric acid, and instead of reacting with nitric acid, we react it with nitrous acid, so this is HNO2, in the presence of sulfuric acid. All right, so what happens here is that we get what's known as a diazonium salt. And so this diazonium salt, as you can see, is a highly reactive species. It has a nitrogen-nitrogen triple bond inside. And so this makes it very reactive because the leaving group could be nitrogen gas. Okay, so how does this reaction work? Well, the first thing that we're going to do is to form our electrophile. So we have nitrous acid, and nitrous acid can react with sulfuric acid, right, to give us some electrophile. And so the first thing we're going to do is to protonate the nitrous acid. Right, so just like this, we protonate the nitrous acid to give us this species, which then collapses with loss of water to give us the nitrosonium ion. And this nitrosonium ion has two resonance forms. You've got a nitrogen triple bonded to oxygen with a positive charge on oxygen, and then the other resonance form has a positive charge on nitrogen without an octet. Okay, so it's this particular form that is going to then react with the aniline. And so let's get that thing to react with the aniline. This is our electrophile, but it's not going to react at the benzene ring. This time it's going to react at the nitrogen itself. And so nitrogen is then going to attack the nitrosonium ion. You're going to get an intermediate that looks like this. Okay, so we've got positively charged nitrogen species. It's going to lose a proton to generate a neutral species. And this is an example of a nitrosamine. So nitrosamines are very toxic. And so this is what happens when you have grilled meats. They contain a lot of nitrosamines. This nitrosamine can tautomerize, and the tautomeric form allows us to see how we might generate that diazonium salt. And so the tautomerism gives us this species, and look what we have. We have a nitrogen-nitrogen double bond. And so what can happen next is that we can get another proton to attack. And so proton attaches to the oxygen lone pair, and then we get a good leaving group. And that good leaving group can, of course, lose water. Nitrogen lone pairs can kick in, water kicks out, and what you're left with is the diazonium salt. And so this diazonium salt is an intermediate in a variety of syntheses. We don't actually isolate the diazonium salt. They're important synthetic intermediates because they're electrophilic. And there are two positions in which they're electrophilic. One position is they're electrophilic at that nitrogen, but they're also electrophilic at that carbon atom. All right, so let's see how they're going to react at both of those types of positions. Okay, so if we have the diazonium salt, and we react this diazonium salt with some nucleophile. Let's say that this nucleophile happens to be a aromatic, ring. In particular, you have to have a nucleophilic aromatic ring. So let's increase the HOMO by placing an oxygen atom on it. So we have phenol here, and we're going to react this with the diazonium salt, and it's going to react at the terminal nitrogen. And so the way we get this to react is you can think of the diazonium salt as being the E+. We're going to get electrophilic aromatic substitution at the nitrogen atom. And so what we end up with is an intermediate that looks like this. And then we get loss of the proton to reestablish aromaticity, and the net result is that we have a species that has this nitrogen-nitrogen double bond inside. And this is a molecule called an azo di. Right? And so this has a lot of conjugation. And so because it has a lot of conjugation, it's going to absorb in the visible wavelength of the electromagnetic spectrum. And so you're going to be able to take two species that don't have any absorption in the visible light region and couple them together to make an azo di. And this happens via an electrophilic aromatic substitution reaction of a nucleophilic arene, like a phenol, plus the diazonium salt that you created from aniline. All right, so this is the electrophilic aromatic substitution-like reactivity. What about the nucleophilic aromatic substitution-like reactivity? Well, diazonium salts also have nucleophilic aromatic substitution reactivity that occurs at the aryl CN bond. So let's talk about that. And we want to show that by kind of drawing this nice little diagram, this nice little pinwheel diagram that shows you all the various types of things that you can react this diazonium salt with. And you're going to do this kind of reaction in the laboratory. So you're going to prepare this diazonium salt, you're going to keep it at low temperature, and then you're going to react it both to make an azo di, but also to make a bond at that carbon atom. So we can kind of think of the nitrogen gas that's embedded within that molecule as being a good leaving group. And so what happens is we can react at that, that starred carbon there with a bunch of different nucleophiles. One nucleophile, for example, could be copper cyanide. And if we react copper cyanide with the diazonium salt, we can get benzonitrile. If we react it with H3PO2, we will reduce that molecule to just benzene. So we're replacing the nitrogen-nitrogen triple bond with a hydrogen. If we react it with water, we can get phenol. And so all of these reactions involve some nucleophile doing a nucleophilic aromatic substitution reaction. Potassium iodide would allow us to incorporate an iodine into the molecule. We haven't had that opportunity yet. KF would allow us to incorporate a fluorine into the molecule. And then we have copper chloride, allows us to make chloroarenes, and then copper bromide allows us to make bromoarenes. So a different way of making the bromo and chloroaromatics. Now some of these reactions have specific names. And so let's talk about some of those reactions and what might the mechanism of these reactions be. And so the first reaction I want to talk about is the reaction with KF, or we could react this molecule also with HBF4. Okay, so let's talk about those. All right, so the first name reaction that we're going to come across here is known as the Schemin reaction. And so the Schemin reaction is a good way to make aryl fluorides. So we're going to take the diazonium salt, again, that we generated from aniline with nitrous acid, and we're going to react it with tetrafluoroboric acid. We're probably going to have to add some heat here. And what happens here is that you're going to get a nucleophilic aromatic substitution mechanism. All right, so we've got this diazonium salt. Our tetrafluoroboric acid is going to look like this. Right, we've got negative charge on boron. We're going to be able to add a fluorine to the benzene ring. That's going to allow us to kick the electrons up onto the carbon atom as a lone pair. So we're going to generate an rhenium ion. So this rhenium ion is going to look like this, where we've got a new carbon-fluorine bond. And we have a good leaving group. And so we said that the leaving group ability had no effect on the reaction. It's fast. The rate determining step was the addition of that fluorine. What happens here is just an elimination, but now we eliminate world's best leaving group, which is nitrogen gas, and then we generate our aryl fluoride. So this is known as the Schemin reaction. Second reaction are all those reactions that involve copper. So this is known as the Sandmeyer reaction. So Sandmeyer reaction is a good source of making aryl chlorides, aryl bromides, and aryl nitriles, and it really operates by that same kind of nucleophilic aromatic substitution mechanism. So we've got our diazonium salt, we've got some counterion here, and we're going to react this with some copper X. So X is equal to chlorine, bromine, or cyanide. And what's going to happen is we're going to get a nucleophilic aromatic substitution mechanism where the copper is going to start to coordinate to that nitrogen, and it's going to allow you to deliver that X group to the aromatic ring. And so we're going to get a nucleophilic aromatic substitution mechanism. We generate an rhenium ion. We have a new X group, and we've of course got this nice little leaving group here, and that leaving group then loses nitrogen gas to give us our new aryl X bond. Okay, so these are two reactions that are name reactions in that series that we had on the previous slide of the diazonium salt. Now there are other types of reactions of benzenes that don't really fit in the category of electrophilic aromatic substitution or nucleophilic aromatic substitution or even reactions of diazonium salts, but nevertheless they are important for functional group manipulation. And so what are some of these? Well, I'm going to give you our list of name reactions. So the next one is called the Clemenson Reduction. So the Clemenson reduction converts an aromatic ketone into an alkyl group. Okay, so if we have this group here, we can, of course, take benzene and react it in a Friedel-Crafts acetylation reaction to give us this ketone. But what if we just wanted to reduce that ketone? Well, we can do a Clemenson reduction, which allows us to use what's known as a zinc amalgam. So this is a zinc-mercury mixture in the presence of HCl, and what will happen is you will reduce that ketone all the way down to the alkyl group. All right, so you're essentially removing the oxygen. Right? So this Clemenson reduction is a really important one because it allows us to put primary centers onto benzene rings. So this would happen in a two-step process. You would first take benzene, react it with the acyl chloride to generate the ketone, and then reduce the ketone via Clemenson reduction to give you the alkyl chain. You can also do this with what's known as a Wolff-Kishner reaction, or Wolff-Kishner reduction. This is the same kind of thing, just uses a different set of reagents. And so in this case, you're going to start with an aromatic ketone. This time we're going to use what's known as hydrazine and KOH. So hydrazine is just two NH2s strung together. And again, the resultant product is that you're going to reduce that ketone to an alkyl chain. Now, another direction you could go is the opposite direction. So what if you wanted to take an alkyl chain and convert it into something that's highly oxidized? Well, you can do that via an oxidation of alkyl chains. So let's talk about that. All right. So this isn't exactly a name reaction, but I'll put it in the list. Okay. So oxidation. So you can oxidize methyl groups, and you can oxidize other alkyl groups using chromium reagents. And so let's say we have toluene here. If we react toluene with sodium chromate in the presence of sulfuric acid, you're going to get a fully oxidized species. So we're going to get a carboxylic acid out of this. Now the other set of reagents that you could use are KMNO4 and sulfuric acid. Does the same kind of thing. But the product of this reaction is going to be the carboxylic acid. So you're exchanging the 3 CH bonds for 3 carbon-oxygen bonds. Now what if you just had, instead of a methyl group, you had some sort of alkyl chain? So let's say we started, instead of with methyl, we started with ethyl. You no longer have 3 CH bonds, you have 2 CH bonds and a CC bond. So what if we were to react the same set of reagents, sodium chromate, with sulfuric acid? You're only going to oxidize the 2 CH bonds. So what you're going to do is to convert that alkyl chain back into the ketone. So you're going to replace the 2 CH bonds that are adjacent to it with a doubly bonded oxygen, 2 bonds to oxygen. Now the next set of reactions is known as the Birch reduction. Now Birch reduction allows you to reduce aromatic rings. And so the two reactions that I'm going to draw here are one that has an electron donating group on it, like an isopropyl group, and one that has a electron withdrawing group on it, like a CF3 group. And what we do here is treat this reaction with dissolving metal reduction. Okay, so we're going to take sodium and ammonia. And what you'll notice is that the distribution of products is a little bit different. So let me draw those products out. And what you'll notice is that the double bonds are at different positions depending on whether it's electron donating or electron withdrawing. So both of these groups are reduced aromatics, so they're 1,4 cyclohexadienes. And what you'll also notice is that the electron donating groups will yield a product in which the substituent, the isopropyl in this case, will lie on the double bond, right? While the electron withdrawing group will reduce that benzene ring so that the substituent is not directly attached to that double bond, right? So the difference here is between the isopropyl group being on the benzene, on the double bond, versus the CF3 not being directly attached to that sp2 hybridized center. And so this is a way of getting these 1,4-cyclohexadiene products. Remember that benzene rings are very, very difficult to reduce. This is a very challenging reaction, and so you really need very powerful conditions in order to overcome that aromatic stabilization energy. And well, you do that by making the benzene or making the aromatic itself swim in a sea of electrons, and that's what happens when you have sodium metal around. Okay. The reaction are the reductions of the nitro groups. So this is number 7. And again, this doesn't have a name, but we can reduce nitro groups to anilines. And so let's say we took a benzene ring and attached a nitro group on there using a nitration reaction, right? Nitric acid and sulfuric acid. But then we wanted to take that nitro group and reduce it to the amine. There are 2 ways that you can do this. Tin HCl, or you could use iron HCl. And what that will do is it will reduce the nitro group all the way to the aniline. Well, this is important if you wanted to take something that was deactivating on the benzene ring and convert it into something that's activating on the benzene ring. And then finally, we're going to talk about the acetylation and deacetylation of aniline. Okay. Now we know that an amine group is highly, highly activating. And so if you were to react this molecule with bromine, it would tribrominate at the ortho and para positions. So what if we wanted to temper this reactivity? Well, the way we do that is by acetylating it. Right? So this one will overreact with electrophiles. Right? So it's going to tribrominate, trinitrate, trisulfonylate. Well, what we can do is we can temper that reactivity by reacting it with an acetylating reagent. Right? So this is acetic anhydride. In the presence of pyridine as solvent, what you can do is you can generate the amide. And now this amide will only mono react, mono electrophilic aromatic substitution. All right, so this one reacts only once with an electrophile. Okay, and that's because that's less activating than the amino group is. Now, of course, if you wanted to take the aniline, temper the reactivity by reacting it with acetic anhydride, then do an electrophilic aromatic substitution to install one functional group, but then you wanted to take that acetyl group back off, there are 2 ways that you can do that. Right, one way you can do that is by reacting it with sulfuric acid and water, a little bit of heat. Right, or you could do it with strongly forcing basic conditions, so KOH, water, and heat. And this will remove the acetyl group to give you the free amine again. Right, so this is often called a protection scheme. So we protect the nitrogen and then we deprotect it to reveal the amine back. And so those are the reactions of benzenes that often don't involve electrophilic or nucleophilic aromatic substitution reactions.